What's up, guys? John TheMorgile here. Going to do a flat Earth video. We're going to take another look at the world record for long distance landscape photography. If you guys remember, I did a video recently that was called Flat Earth Some Common Sense, where I first featured this really awesome picture. And I'll put a card right here to that video in case you missed it. And I'm going to take another look at the same image in a little bit different light. Now, of course, we did the typical standard curvature calculations to see how much of that mountain range should have been obscured by the curvature of the Earth according to the heliocentric model. And of course, we can see the entire mountain range where over a half a mile of the very tip top of the tallest peak should have been obscured by the horizon. Another really important point that I want to expand upon a bit, uh, just very briefly, that I raised in that video is the entire metabunk claim to this thing called standard refraction, where, of course, the globies and the normies try to use refraction in the maximum possible extent, always in favor of a spherical Earth, but it's really beyond asinine to try to use refraction in an argument related to the curvature of the Earth in terms of an observer looking way over across a body of water, say from this altitude of 2,000 meters, seeing a peak that's over 273 miles away. And the reason that the first reason that refraction or standard refraction, which is just ridiculous because there is no such thing as standard refraction, refraction is a variable that can affect how light behaves to varying degrees. And to say that there's a standard refraction that just so happens to be the maximum possible allowance for refraction, always in favor for the globe. First of all, it seems that they've got it backwards, as refraction will cause objects to apparently drop vertically and not rise up vertically. What I'm going to do real quick is play a clip from a fairly well-known flat Earth proponent, Rob Skiba, and I'll put a link to this original video in the description because he's done a really good job demonstrating how refraction indeed causes inbound light to drop and not to rise. And this is the same exact findings that Dr. Zach and his team working with Cinema 4D found, that inbound light from the stars as well as the sun is, yes, it indeed is refracted by the atmosphere, but that causes the object to apparently be lower than the object actually is. And so for metabunk and for people to claim refraction always works in favor to make the flat Earth, or I'm sorry, to make the globe Earth appear to be flat is ridiculous. They say that it causes distant cityscapes and mountains to raise up above the horizon line because of refraction. But again, this is bass backwards. All experiments that have been done to study refraction show that yes, light does indeed bend through different media, through different temperatures, through different types of gases and atmosphere, as well as magnetic fields, and possibly unknown variables that we aren't even aware of, like ionized plasma. However, as sort of a rule of thumb, when light is refracted here on Earth in reality, the light waves apparently drop. They don't raise up objects apparently, and so we can fairly well say to leave refraction out of this altogether because they've got it bass backwards. But then again, you also have, again, the double dropping away effect if the Earth was a globe. You'd have apparent dropping away due to perspective, and you'd have actual dropping away due to vertical descent. And to say that refraction is going to somehow solve both of those problems and make the Earth appear to be a plane and cause 273-mile distant peaks to raise up, uh, you know, a couple miles is just absurd. So just quickly dissecting these two diagrams here, what you're seeing is not to scale, but it's a representation of what I'm trying to convey. This first image here shows perspective upon a plane. All of those vertical red lines are intended to be of the same height. And of course, looking at it from a side view, it looks like they're getting shorter and shorter. That's not what I'm intending to show. What I'm intending to show is how, to that observer, looking at those vertical lines from his perspective, they will appear to drop lower and lower. And so, this is the only way to draw it from a side view. If you drew it from a side view, all of those lines would be the same height, but according to that observer, they get smaller and smaller as they get off, further in the distance. Now, that's what we see upon a plane. However, if the Earth was a sphere, we would necessarily see that apparent vertical diminution of objects due to perspective on top of or coupled with the actual vertical descent due to curvature. And again, this is why I say trying to bring refraction into this conversation is ridiculous, because even if you give the refraction, 100% of its possible effect on light, and assuming that it somehow favors a globe in all instances, which is preposterous, then it absolutely would not account for the apparent diminution in size due to perspective, nor would it account for the actual dropping away due to curvature of the Earth, and it certainly wouldn't negate or nullify the apparent diminution in size due to perspective and the actual diminution in objects' height due to curvature. So there you have that, metabunk people. Using that calculator is just absurd. Using anything called standard refraction is absurd, especially with all of this in mind. So let me just run this clip real quick that comes from Rob Skiba's channel. I'll put a link in the descriptions and a card in case you guys haven't seen this one. It's really interesting. I'm just going to play a clip. I'm not going to play the whole thing, and I hope Rob doesn't mind. But again, I will put links to the video in the description as well as a card and all that stuff so you guys can find this video.
If the atmosphere, especially over water, is made up of zillions and zillions of tiny convex drops of water, then collectively perhaps they all combine to make one big convex lens, in which case it would act like a magnifying glass. Okay, so with that in mind, let's look up some websites dealing with the refraction of light. You might see a graphic something like this, showing light bending downward, just like the weatherman guy said. And here's your typical graphic showing how light rays entering some sort of medium, like in this case water, refraction causes the light to bend downward. Now we've all seen pictures of, a pencil or something in a glass of water, and how not only does refraction bend the image downward, it also magnifies it. I'm going to say that again. Water causes refraction, bending the image downward, and magnifies it. So this is important now. So now back to another clip from that previous video. Let's entertain for a moment the completely absurd notion that water is flat and it always seeks its own level. We're looking across a flat plane of water, 46 miles across. I really do believe that, just like the experts said, the globalist guys, these are people who believe in the globe now. They are the ones that said, hey, the atmosphere really is acting like a lens, and they put a lens in front of the camera to show how it works. So I'm just doing what they're doing. I'm using the same logic that they're using, the same science that they're using. And, science is all about testable, observable, and repeatable data, right? So to alleviate the problem of distorting the edges because the magnifying glass ring is too small, I went on Amazon and I got these plastic magnifying sheets and came up with another way of doing the same thing using the sheet right here. Set the city up, a little cutout of the city, and now I've got the big magnifying glass sheet. Bring the camera right up to the lens. See, that's the normal view of the city. Now let's back up again.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here,
The atmosphere really is acting like a lens.
yes.
Atmosphere really is acting like a lens, and this is how much of the city is missing due to the lensing effect, the magnification of the atmosphere. You're missing a good portion of the city just by pulling my iPhone back on a 3 foot long desk. That's how much I lost of the city. And as with any scientific experiment, you always try to improve upon what you did before. So I got some foam core, made a little housing for the magnifying sheet, and pasted the city on the back there. And I made it as two separate pieces so that I could flex it as necessary, because I think that there are different types of atmospheric conditions that would allow for more magnification versus less magnification. So in this scenario, you have more magnification, and in this one you have less. And for this one I decided to put the Toronto skyline into my little box here. And let's try it again. Okay, we're all the way up against the glass. Now let's zoom across the lake. And wow, look at that. The lower portions start to disappear. Now let's zoom back in to get a little closer to the one that Captain Baltard was talking about here. And wow, look at this. Here's his image on the right, and here's my image on the left. Missing the lower portions of the city had nothing to do with curvature whatsoever. And this, of course, is my answer to the meme that you've all seen being passed around on Facebook showing the missing part of buildings is absolute proof of the curve. No, not really. But okay, here's the part I really wanted to show you guys. I was already in the process of modifying my experiment, so here's what I came up with. I've got my magnifying sheet frame, and I created a little stand to paste the sun on it and keep it the same height over the flat surface of a table. So the sun is always going to be parallel with the surface. And check this out. All right, here's the first test of a sun moving over a flat surface, and with no atmospheric magnification, it does what we might expect it would. It gets smaller as it goes away from us. All right, now let's see what happens when we add in our atmospheric magnification. Again, water and refraction. Water causes magnification and refraction, right? So let's bring the sun back. Oh, check this out. Refraction bends the light downward. It made the sun set on a parallel surface as it was moving parallel, the same height, the whole way over a flat surface. The refraction caused the sun to set.
So this is exactly what I'm talking about, that atmospheric refraction or lensing or just refraction in general causes light, especially celestial light, to drop proportionally with distance from the observer, and reflected lights coming from a distant cityscape, refraction or atmospheric lensing, also causes light rays to drop. And so to say that refraction helps the globe theory in any way is just completely wrong. It's backwards. But even just giving them refraction for argument's sake, when you see that what we're actually seeing on a flat Earth in terms of distant ships appearing to drop and losing the bottoms of distant cityscapes, that's what we're seeing there is the operation of perspective, which again happens within the eye, on a plane. And so if the Earth was curved, you would have the operation of perspective happening within the eye, on top of actual vertical descent due to curvature. And so I know that I'm repeating myself a bit here, but this is why not only is refraction irrelevant, but refraction is working against the globe. So the fact that we can see this 4,000 meter tall mountain from 273 miles away proves the Earth isn't a globe. There's no curvature. And by the way, in case you didn't know, in order for the Earth to be a ball, it would have to have curvature. And so even just not even considering refraction just for a moment here, so just refraction aside, what we're looking at in terms of distant objects shrinking proportionally with their distance is the actual operation of perspective, which occurs within inside of our eye. So that distant peak that's 273 miles away isn't actually 2 inches tall or whatever. It just appears that way because of perspective. It's because our eyes are convex lenses and the light enters our eye through the pupil, it gets inverted, and angular size diminishes with distance, and so therefore objects that are further and further distant will appear smaller. Now, another natural operation of perspective when you're standing upon the physical plane is that as objects go beyond your horizon or beyond the so-called vanishing point, they will continue to diminish in size equidistantly from top to bottom. So they will squish equidistantly down the same exact rate as they are squishing up. However, you can't see what's below the horizon line, and so it appears as if the object is merely squishing from the top down only. But of course, we know that it is squishing equidistantly or proportionately from the center, up from the bottom, and down from the top. So if you can humor this diagram here just for a bit, no, it's not to scale, it's not perfect, and yes, I could have drawn it a little bit differently, but I've just added in the apparent horizon for this observer here, which means that sort of curved line, dotted line that I've put in there would represent according to this observer, where the sky meets the plane, or where the sky meets the sea, or where the sky meets the ground, basically. And so anything beyond that point, even though the object is obviously taller than he is, at a certain distance beyond the horizon, that object is going to continue to diminish in apparent vertical angular size beyond the horizon, although it's only going to appear to diminish from the top down because, again, you cannot see through the ground. And I hope that points made very clear, and this is one of the main reasons why distant ships appear to, drop bottom first is because of perspective, and also, as Rob Skiba had mentioned, it has to do with atmospheric lensing. Now, I sort of disagree with him on one minor, really it's just a semantical thing. He said all the water droplets make up a convex lens when put together, which, yeah, I definitely see what he's saying with that, but the atmosphere itself is more or less transparent. We can see right through it at close distances, but once you get to really, really quite long distances, the atmosphere as a whole becomes opaque, which we can clearly see, the blue sky during the daytime. The atmosphere becomes opaque at a specific distance, and that distance is going to necessarily be an equidistance all around you. Now, of course, the ground isn't going to be a bubble around you. The ground is a flat line that is an impenetrable, opaque barrier to your line of sight. Whereas the atmosphere or the atmosphere itself is going to necessarily form sort of a dome shape around you subjectively, made of water vapor, yes, and perhaps the fact that each little particle of water vapor is a spherical sort of convex object that may have something to do with it, but I just think that it more has to do with the distant atmosphere adding up to become an equidistant bubble around the observer. That bubble is indeed made of water vapor and other gases, and so it makes perfect sense what Rob's saying. I agree with him 100%. And perhaps he's right. Perhaps it is the shape of the water vapor bubbles that aids in this. However, I believe that medium could be made of anything. It could be like he used a sheet of magnifying material, or a magnifying glass, or water vapor, or even a magnetic field could have, similar effects or play weird effects on light waves. But yeah, definitely onto something here, and hopefully you guys see what I mean between refraction being irrelevant to Globehead's arguments that, first of all, refraction works in the opposite direction which they claim. It makes light waves drop. Second of all, refraction does not account for the apparent vertical diminution of objects proportionally with distance due to perspective, nor does it account for the alleged expected dropping away of objects due to Earth curvature, and it certainly doesn't account, refraction that is, certainly doesn't account for the actual dropping away due to curvature plus the apparent dropping away due to perspective. Okay, so what we're seeing in real life is perspective upon a plane that causes objects to appear to go down a curve. Now, if we also lived on a sphere, then you would have actual vertical descent due to curvature, plus you would also have apparent diminution in size of objects proportional with distance. And so you would have a double effect of vertical descent due to curvature and apparent vertical descent due to perspective. And so to say that, well, but refraction is ridiculous, even if you hand them standard refraction, which is preposterous, for argument's sake, it will have such a little effect on not only the expected vertical descent due to curvature alone, nor would it have a very big effect on apparent vertical diminution of an object, downward due to perspective, but you have to combine those things. And so to say that refraction is somehow going to magically make a mountain raise above the horizon line like 3 miles is ridiculous. Because again, the mountain itself in the distance is 2.55 miles tall, and then the horizon, according to the curvature calculations, the horizon should obscure that mountain with an extra over half-mile to spare. So you should not be able to see the tip top of that mountain, even considering refraction, especially because refraction causes objects to apparently drop and not raise, but also because we should expect to see actual vertical descent due to inverse square curvature. And we should also see the operation of perspective, which would be added together or maybe even multiplied together to make it absolutely ridiculous to try to argue refraction in terms of the curvature calculations. Now, as promised, I'm going to take another slightly different look at this world record landscape distance photography photo in a little bit different light, but I also just wanted to mention that I think we should be using eccentricity-based mathematics in this instance because we're dealing with the actual alleged shape of the sphere as opposed to dealing with a single point looking parallel to the sphere, which becomes a tangent to that curve, which is what we use for the 8 inches per mile squared. And so I just want to make it clear that this next part of what I'm doing is using the 8 inches per mile squared calculations, although it's very likely that we should be using a completely different curvature calculation for looking at actual convexity or like the frowning effect of distant, say, 70-mile stretches of mountain ranges. That again, every straight line on a sphere should be curved, and so hopefully even just using the 8 inches per mile square calculation over a 70-mile distance horizontally across the horizon, which is of course 100% flat even from 273 miles away. If you're testing the theory that the Earth is a sphere, none of this adds up, doesn't match up to observation. Eccentricity-based mathematics is dealing more with the shape of an object as opposed to the regular standard curvature calculation that we're all familiar with, which is 8 inches per mile squared, is dealing with a tangent away from the curve of the Earth. And so maybe one way to put eccentricity-based mathematics into practice, or at least sort of explain it, because obviously I can't put it into practice. I don't fully understand it, and however, I am in contact with somebody who does and uses and applies eccentricity-based mathematics in everyday life for tangible, realistic physical results that rely on the mathematics to be exact. And so one way to put it would be that a perfect sphere has zero eccentricity, whereas, say, an oblong shape would have, some other ratio, some off ratio of eccentricity, as opposed to a sphere, which is 1 to 1 or zero eccentricity. And so, in this regard, if you can think of drawing out a circle using a compass, and in order to use a compass, you put the needle directly in the center. You adjust the radius of the circle by widening or shortening the angle of the compass, and then you just you draw a perfect circle around that center point. And so if you were just to imagine whatever the increments of unit is, say it's 25,000 miles, or say it's 25 inches, or say it's 25 millimeters, regardless of the units of measurement, what's going to happen is, and we'll just use 25 miles as an example first. What's going to happen is if you use a compass to draw a perfect 25,000 mile circumference circle, for every distance that you move that pencil along that perfect curve, it's going to drop in terms of the actual eccentricity, or the shape of that object is going to drop at a 1 to 1 ratio. So if it's a 25,000 mile circumference, for every unit forward you go, you're going to drop that much. And so if you walk 1 mile at a time all the way around the spherical Earth, you're going to have walked 25,000 miles around, and you're going to have walked 25,000 miles of curvature. And so in this is sort of my layman explanation of how eccentricity-based mathematics can be applied to spherical objects, and it's a 1 to 1 ratio as opposed to the 8 inches per mile squared, which again is a good formula, but the 8 inches per mile squared is dealing with a single observation point and measuring vertical descent from that point compared to a tangent line from the curve, whereas eccentricity-based mathematics is describing a perfect sphere or even a perfect circle, in a two-dimensional sense, as a 1 to 1 ratio of forward motion to horizontal descent. And so just keep that in the back of your mind as we go through these slides. Now, what I've done to take this sort of a step further is to look at, because there is a little bit of argument or debate going on in terms of, yes, we all agree in vertical descent dropping away from you due to curvature, right? But what I'm talking about is vertical descent sort of like, in a frowning effect. And that frowning or convexity to any straight line on a curved Earth would necessarily be a curve. So, in other words, any straight line following a spherical object is necessarily a curved line. And so, what I've done here is taken a look at this from a few different perspectives. So let's get into each one of these slides in a little bit more detail. So again, this picture is called Pic de Fenestrellas, Pic Gaspard Ecrins, 443 kilometers or 273 miles. It is the silhouette of Bar de Crins, 4,102 meters tall. Towards the middle left of the image, that's the tallest peak from Pic Fenestrellas, which is 20 meters tall. Before sunrise on the ground, I would imagine, because we do see an instance of the sun there. I would suppose that's because you're so high up. So it's certainly the twilight time of day in the Terminator area, if you will. And putting some scale to this thing, the second slide here, you can see that we know that the mountain is 4,102 meters tall at the highest peak. which translates to 13,458 feet, or 2.55 miles above sea level at the peak. And so, in knowing that, it might not be 100% perfect, okay, but we can get a pretty good scale. And although there may be some atmospheric lensing involved, so those mountains may appear larger or magnified due to atmospheric lensing, which is not a theory, it's a thing that actually happens, we can still use that as a scale across the horizon. Especially considering the fact that if these mountains are indeed being magnified, then it's erring on the side of caution for the globe anyway. Because if the mountains were, say, much smaller in appearance, but we could still see the whole thing on the flat Earth, so there was no atmospheric lensing involved, then the distance across, from left to right would be much more than 70 miles. So this is erring on the side of caution, even assuming that there is some atmospheric lensing going on, which there almost certainly would be with that much distance of low-lying, thick atmosphere, much of which is above water. So, just to give you the scale, and I used InDesign precision measuring lines to get it as close as possible to scale. So, 2.55 miles, which is the height of that peak, is about 0.6 inches on this document. And you can translate that to a single inch equals 4.25 miles to scale. And so the next slide, we'll just sort of apply this. And again, it's not perfect, but if 1 inch is 4.25 miles, then the 16.67 inches across the horizon multiplied by 4.25 is approximately 70.85 miles. Well, you could just go ahead and round it off and say 70, but that is 70 miles of horizon based on the fully visible mountain, which we know from base to peak is about 2.55 miles tall. And again, even if there is some lensing effect going on, we can still use that as a scale for the horizon, because the horizon clearly ends at a point closer to the mountains, but we can clearly see the base of the mountains. So, I mean, this picture here is very, very good evidence that the Earth is a plane. All of those lines that are running across the water should all be slightly curved, and we can see that they are waves traveling across a plane of water. This is a vast, vast expanse of visibility, because yes, the observer here has a high altitude and the target object is also high in altitude, but the expected curvature, the expected vertical descent due to curvature, is not there. What we're seeing is perspective and a bit of atmospheric lensing, but we're seeing perspective. And so if the Earth was a globe, we'd be seeing perspective and actual vertical descent due to curvature of that mountain range in the distance. Now, one thing you'll just notice is that that center point, if we're assuming that we're standing right, dead, if that's the dead center of the observer's viewpoint, it should be about 837 feet taller than either side. So just call A the center and B and C the sides. To scale, A should be about 0.037 inches higher, which really ain't much, but it would be noticeable. And again, that would amount to 837 feet higher, or 0.158 miles higher at the center than it is on the sides at B and C. And the reason that we get this is because, yes, it is 70 miles, and so your gut instinct is going to be to square 70 and then multiply that by 8 inches, or 0.666666 feet, in order to get that expected curvature. But again, I think that that formula is not accurately being applied to the shape of the Earth. That formula is to figure out what your line of sight would be in terms of a tangent to the curve of the Earth. So it is, this is certainly certainly erring on the side of caution in terms of the globe. Now, this next slide shows the perfect horizontal line, which obviously matches up. And I'll zoom as much in as I can. I know it'll lose some resolution, but the horizontal line, the perfectly horizontal line, which is the black line, lines up perfectly to the horizon. Go figure, right? It's sort of a no-brainer. The word horizon and horizontal are literally synonymous, and they are roots of one another. The root of horizontal is horizon, so it should not be a big surprise that the horizon is completely horizontal. But the cyan or light blue line is curved to 836 feet. And it is definitely a noticeable curve when you zoom in on it relative to the perfectly horizontal line. And so, again, this is sort of the frowning effect that we should see when we're looking across roughly 70 miles of horizon. And we can see the entire base of those peaks. Although there may be a bit of refraction towards the bottom, we can clearly see the entire mountain range. And again, according to the basic curvature formula, the tip top of the tallest peak should be buried by over a half a mile of that horizon line. And to claim that refraction would pull those mountains up, I don't know, 3 miles is preposterous for multiple reasons. And again, those reasons are what we're actually seeing is perspective. If the Earth was a globe, we'd see perspective plus vertical descent, and refraction works in the opposite direction. But even handing them refraction, there is no such thing as standard refraction, even if it worked in the favor of the globe, which it doesn't. But it would not account for or nullify the vertical descent due to curvature plus the apparent vertical descent due to the operation of perspective. So anyone that tries to bring refraction into this argument is just absolutely grasping at straws, trying to fall back into the matrix and refusing to deal with their cognitive dissonance. Now, this is 107.5 degrees angle of sight. So if you were actually up there standing there looking at this, you'd get about 13 more degrees, so a little bit on either side. So you could even do a little bit further than 70 miles at this altitude. And on the next slide, what we're going to do is a little bit different. Let's assume that you were standing directly all the way to the left, which you'd have to move a little bit over to the left in order to be at that spot. But seeing how the horizon is perfectly horizontal, it's sort of irrelevant. We can just say, okay, well, let's just do this with the whole 70 miles. Well, then, comparing the far right to the far left, the far right should be about 3,267 feet lower than the left side. Or you could do this vice versa from the right side to the left. And that would equate to about 0.62 miles. And that boils down to 0.15 inches to scale in this diagram. It appears we have found satellites attached to weather balloons. Well, isn't that a big surprise? We've only been saying that for a couple years, that if there are such things as satellites, they are geostationary weather balloons. And people are like, well, that's impossible. They couldn't, you know how much it would cost to put up all those weather balloons? Yeah, well, NASA itself gets $20 billion a year. I think they can afford some pretty good weather balloons. And by the way, it's much, much cheaper to put up a weather balloon than it is to put up a satellite, which you can't even do because the Earth isn't a globe and you can't orbit a motionless plane. Even if you could put satellites up 22,000 miles into the air where they claim the geostationary ones are, radio frequency waves would attenuate into the background radiation well before 22,000 miles. So if you think the little Uber Gennaro plastic dish attached to the side of your house is actually communicating with a satellite, you are sadly mistaken. Thanks for watching, everybody. If you'd like to support this channel, you can do so direct through PayPal to www.paypal.me/TheMorgile1 or through Patreon for as little as $1 a month. That's www.patreon.com/TheMorgile. I'll put links in the description. God bless you all. Thanks for watching. Spread the word, spread the world, and peace. Really good job demonstrating how refraction indeed causes inbound light to drop and not to rise. And this is the same exact findings that Dr. Zach and his team working with Cinema 4D found, that inbound light from the stars as well as the sun is, yes, it indeed is refracted by the atmosphere, but that causes the object to apparently be lower than the object actually is. And so for you know Metabunk and for people to claim refraction always works in favor to make the flat Earth, or I'm sorry, to make the globe Earth appear to be flat is ridiculous. They say that it causes distant cityscapes and mountains to raise up above the horizon line because of refraction. But again, this is bass-ackwards. All experiments that have been done to study refraction show that yes, light does indeed bend through different media, through different temperatures, through different types of gases and atmosphere, as well as magnetic fields, and possibly unknown variables that we aren't even aware of, like ionized plasma. However, as sort of a rule of thumb, when light is refracted here on Earth in reality, the light waves apparently drop. They don't raise up objects apparently, and so we can fairly well say to leave refraction out of this altogether because they've got it bass-ackwards. But then again, you also have, again, the double dropping away effect if the Earth was a globe. You'd have apparent dropping away due to perspective, and you'd have actual dropping away due to vertical descent. And to say that refraction is going to somehow solve both of them, of course, we did the typical standard curvature calculations to see how much of that mountain range should have been obscured by the curvature of the Earth according to the heliocentric model. And of course, we can see the entire mountain range where over a half a mile of the very tip top of the tallest peak should have been obscured by the horizon. Another really important point that I want to expand upon a bit, just very briefly, that I raised in that video is the entire Metabunk claim to this thing called standard refraction, where, of course, the globies and the normies try to use refraction in the maximum possible extent, always in favor of a spherical Earth, but it's really beyond asinine to try to use refraction in an argument related to the curvature of the Earth in terms of an observer looking way over across a body of water, say from this altitude of 2,000 meters, seeing a peak that's over 273 miles away. And the reason that the first reason that refraction or standard refraction, which is just ridiculous because there is no such thing as standard refraction, refraction is a variable that can affect how light behaves to varying degrees. And to say that there's a standard refraction that just so happens to be the maximum possible allowance for refraction, always in favor for the globe. First of all, it seems that they've got it backwards, as refraction will cause objects objects to apparently drop vertically and not rise up vertically. What I'm going to do real quick is play a clip from a fairly well-known flat Earth proponent, Rob Skiba, and I'll put a link to this original video in the description because he's done a What's up, guys? John TheMorgile here, going to do a flat Earth video. We're going to take another look at the world record for long distance landscape photography. If you guys remember, I did a video recently that was called Flat Earth, Some Common Sense, where I first featured this really awesome picture, and I'll put a card right here to that video in case you missed it. And I'm going to take another look at the same image in a little bit different light. Now,